Hello, Longhorns. Today we're going to dive into a different section of waves. We've been talking about mechanical waves, and if you remember, mechanical waves require a medium. This new section, we're going to take a look at light. Light is going to be a little bit different. Though it still transfers energy, it doesn't necessarily require as much. So, this is lesson 17. We're coming from pages 444 through 448 in your textbook. When we talk about characteristics of light, light is an electromagnetic wave. If you take a look at this word, you should be able to break it down and figure out some of the parts that look familiar. For electro, it probably reminds you of the term electricity. And of course, magnetic, you start to think of magnets. The biggest difference between a mechanical wave and an electromagnetic wave is this type does not require a medium. So light does not require a medium, which is why there are areas of light in space. It's also the reason that you do not hear sound in space, because sound is mechanical and it does require a medium. There are several different types of electromagnetic waves. So when you're thinking of light, I want you to go beyond just a light bulb that's in your home or your classroom. We're also going to look at radio waves, microwaves, the infrared rays that are used by your remote, those areas that we can see, and this is where your rainbow will fall. We have UV light, your ultraviolet light, your X-rays, and also your gamma rays. So there are different uses for each type of electromagnetic wave. How do you tell the difference? It's based on wavelength. So the longer or the shorter the wavelength will help us determine where on the spectrum these types of waves will fall. Now, you've heard me ask this question before. Are rainbows real? And by now, most of you guys will say, no, they're an optical illusion. We've learned that light has the ability to pass through a prism, or in this case, a raindrop, and it's going to be broken down into colors. Your colors will always appear in the same order, Roy G. Biv. So red, your orange, yellow, green, blue, indigo, and violet. And when you're thinking about the word indigo, I want you to picture a really deep purple or a purplish blue is what they're going for. Here's another picture where we're using scans to figure out areas of heat. So where's energy being transferred to? Keep in the back of your mind that your energy is neither created or destroyed. It's simply going to transfer from one form or transform from one form to the other. Here's an example of what the side of a subject would look like before cell phone usage. And this is after about 7 minutes of cell phone usage. You'll notice in this area we have a lot more red, and it means that there's been an increase in activity or heat. You will also notice that at the back of the brain, you have increased blue before, but decreased amount in that same area. And it's because really you're stimulating different areas. The more a cell has to move, the more heat it will generate. Now, your electromagnetic waves are going to vary based on frequency and wavelength. Don't forget that frequency is represented by a lowercase f, and it's measured in hertz. Wavelength is measured in meters and represented by the variable lambda, which is your upside down y. These do not require matter in order to be transferred, so no medium is necessary. And of course, most of our waves are going to be created by electric charges that are vibrating. So it's that action that will make the biggest difference for this type of waves. All electromagnetic waves are going to move at the speed of light. So far, we've found nothing that moves faster than this speed, and it's 3 times 10 to the 8th meters per second. This is our new constant for this particular unit. So if we think about it, that's a pretty big number. We're out of the thousands, you're coming to the millions and going a little bit beyond as far as speed. And we'll use this to explain why we're able to see certain stars, but not others. Why we have planets that are able to give off a glow and not others as well. Here's your new equation for wave speed. We use the letter c for the speed of light. So lowercase c will always represent 3 times 10 to the 8th meters per second. We have lowercase f, which is your frequency, and then our wavelength symbol, which is also measured in meters. Let's try this equation. Example number 1. What is the frequency of an electromagnetic wave if it has a wavelength of 1 kilometer? Even in this case, we have to be very observant of our units. Whenever we see anything that is not in meters, the first thing I want you to think is, yes, we're going to convert. Let's use our guess method and identify the information that we were given in this problem. So, first things first, we've been told that it has a wavelength, there's my variable, of 1.0 kilometer. And we are looking for the frequency. Your equation in this particular example is C equals F times lambda. Remember that C is a constant, so we already know that C stands for 3 times 10 to the 8th power, and that exponent is positive. We do have a little converting that needs to take place. So we have 1 kilometer. For every 1 kilometer, I have 1,000 meters. So that's what we're going to use as a part of our problem. It's time to solve. We're going to plug in. We start with our original equation. C is going to be 3 times 10 to the 8th power. F is your unknown, so we're going to plug in our variable. And for wavelength, don't forget, we're going to use the 1,000 meters. We're not going to solve for F. We'll do the opposite of multiplying, which is to divide on both sides. These two will cancel out, and F is going to be left by itself. Now, I want you guys to be careful. If you turn this into a whole number, you're able to cancel out your zeros pretty quickly. But if not, use your calculator and be careful that you include parentheses if needed. It does make a difference in our particular style of calculator. So I have 3 times 10 to the 8th, and we're going to divide by 1,000. And you'll notice that the only thing that really changes will be your exponents. So frequency will equal 3 times 10 to the 6th power, and frequency is measured in hertz. Making sure that we've converted everything and paying attention that what needs to cancel out does cancel out will ensure that our calculations are correct. Now, we've learned in this video that light is an electromagnetic wave, which means that we're going toward an area where electricity and magnetism will have a relationship with one another. We've also learned that light does not require a medium, and it's represented by the lowercase letter c. There's also a constant associated with c, which is 3 times 10 to the 8th power meters per second. Nothing moves faster than light. If you have any additional questions, be sure to send me an email. If you would like more information on this topic, you can view this video as well. And I'll see you guys in class.